This is applied physics, subject of applied physics for undergraduate students. The topic is kinematic equations, and we have already gone through definition of displacement, which is the change in the position during some time interval. It is actually a vector quantity, and it has both magnitude and direction. Suppose that we have this coordinate system x and y axis and the origin, and r1 is the position vector at time t is equal to t1, and then it goes to the position r2 here. Then the displacement is delta r. It is in two-dimensional plane given by r2 minus r1, and r2 minus r1 is basically uh, the difference of the x values, x2 minus x1 multiplied by I unit vector, which is a vector along x-axis. It has a magnitude of 1. Then there is y2 minus y1 along the y-axis, and it is multiplied with the j unit vector, which is along the y-axis, and j unit vector has the magnitude equal to 1, direction along y-axis. Delta r, the two-dimensional displacement vector, is shown here by the bold letter, the final position vector minus the initial position vector. Standard international units for the displacement are meters, and the change delta r can be positive or negative resultant vector. So using this definition, we can do many examples, but one simple example is that of the automobile, which is traveling due east on a level road for 32 kilometers. Then it turns due north at a intersection and travels 47 kilometers before stopping. The question is to find the vector that is indicating the resultant location of the car. Let us see. The first displacement is in this figure shown as 32 kilometers due east, and on x-axis the positive x direction is east. Then at this intersection it moves to north. On this plane, the y positive direction is the north. So this is the north direction, 47 kilometers it travels. So a vector and the b vector sum gives you the resultant vector s. We want to find out the resultant vector s, and the resultant has two components, the uh, component along x-axis and the component along y-axis. Since these two vectors are really uh, we can say one dimensional, a vector has only components along the x-axis, and y vector has, this b vector has only components along the y direction, and therefore the resultant vector has the magnitude given by 32 kilometers square plus 47 kilometers square under root due to this what is known as Pythagoras theorem. This triangle has a perpendicular and the base, and the square of the perpendicular value and the base value gives us the magnitude of this in between vector. The magnitude is 32 square plus 47 square under root, and it is 57 value in the kilometers. And then this angle phi is to be discovered, and for this we use the tangent. The tangent is basically the perpendicular value divided by the base. So perpendicular is the magnitude of the perpendicular vector is b, and the magnitude of this vector is a. So b divided by a, which is 47 kilometers divided by 32 kilometers, we get 1.47. Once we have 1.47, then we take the inverse of tangent, for this value. So tangent inverse of 1.47 is 56 degrees. And that's how we have solved the problem of getting this vector S. It has magnitude of 57 and the direction 56 degrees when it is measured from the east. The displacement vector in 3 dimensions has uh, the component along x-axis, the component along the y-axis, and the component along the z-axis. And again, the displacement is actually from r1 vector position at A to the position B, which is r2. So displacement is from vector r1 to vector r2, and the displacement is delta r. Delta r vector is given as r2 minus r1 because r1 plus delta r makes R2. So in terms of the scalar values along x and y and z, it is the difference of x values and difference of y values and the z values. Here x2 minus x1 multiplied by I unit vector along x-axis, and y2 minus y1 multiplied by j unit vector along y direction, and z2 minus z1 uh, difference along the z direction or the k unit vector. Here I, j, and k are the unit vectors along x-axis, y-axis, and z-axis, and we have their magnitude is equal to 1, and these are the differences in the individual x coordinates of the position A and the x coordinate of the position B. Now we come to another important quantity which is used in physics frequently, and that is the velocity. The average velocity is basically the change in position or the displacement divided by the time interval in which this change takes place. Here we have delta t equal to t2 minus t1. Therefore, the average velocity is defined as the displacement delta r divided by the delta t time. This is the average velocity. Displacement is a vector quantity, therefore the average velocity is also a vector quantity. Now another important concept which is frequently employed is the instantaneous velocity. The concept of instantaneous velocity is that we start reducing this delta t to small values, as small as going to 0. So in the limit that the time interval delta t approaches to 0, we write it like this, that the velocity vector, the instantaneous velocity vector, is basically the limit of this thing, the ratio. It is the limit of this ratio when delta t goes to 0. The case is solved in such a manner that this is not going to explode or go to infinity. This will remain finite, and the limit will be taken as the limit is done in mathematics. So delta r over delta t, the limiting case, gives us the instantaneous velocity at time t, and in this case delta t approaches to 0. The direction of this velocity is basically the tangent to the path of the particle, and the above equation is really the definition of the derivative. Since it is the derivative, the first derivative with respect to time, so above equation is basically telling us that the instantaneous velocity at any instant of time is defined as the derivative of displacement vector with respect to time. It is the first derivative. So velocity will be treated as the first derivative of the position uh, displacement vector. The average velocity of the particle in motion is basically delta r over delta t, and it has the dimensions of length divided by time. And the standard international units are, for this case, meters per second, because the length in meters and the time in seconds. The slope of this line on a position time graph is basically the average velocity. If we have a position time graph, the average velocity is just the slope of the line. However, the limiting average velocity as the time interval is reduced to very short values, or delta t goes to zero, then it becomes instantaneous velocity. The instantaneous velocity indicates what is happening at every instant of time, and we are measuring it with the idea that the time interval is reduced to very small value. The average speed is basically a scalar quantity as compared to the average velocity, which is a vector quantity. It has same units as that of the velocity. It is defined as the total distance divided by the total time taken. The average speed has no direction. It is always expressed as a positive value. Neither average velocity nor the average speed gives the details about the trip. The average speed is not the magnitude of the average velocity. For example, a runner which is ending her uh, run again at the starting point, then her displacement is zero. Therefore, her velocity is zero. However, the distance traveled is not zero, so the average speed is not zero. Here we show the instantaneous velocity as the slope of the tangent line on this type of a graph, which is the uh, telling us the distance on one side and the time on the other side. As we reduce the delta, the blue lines are telling us the displacement for the time between T1 and T2, and we see that as we start reducing this delta T, we start approaching this B to very close to A, and eventually the lines are really like the tangent line at the point A, and this blue line is showing that the delta t gets very small. We approach to this green line, which is the tangent line. The slope of the physical data's graph is basically the ratio of the change in the quantity which is on the vertical axis divided by the change in the quantity which is on the horizontal axis. So slope of a graph is really useful. Is it a positive slope or a negative slope? And also it tells us about the velocity. Slope has units unless both the axes have the same units. It will have, for example, on this side if there are meters and on this side if there are seconds, then the slope will have the units of the meters and per second. We come to define another important quantity in physics, which is acceleration. And acceleration is defined as the change in the velocity with time, or it is the basically first we define the average acceleration, which is the change in the velocity vector divided by the time interval in which this change in vector takes place or in which the displacement occurs. So average acceleration is shown by a bold letter and a line on it, which is telling us that this is a vector quantity, and it is given by delta v, the difference of the two velocities divided by the delta t, which is the difference of the two time values. So during the time interval delta t, what is the change in velocity, that is delta v, then the average acceleration is delta v over delta t. The instantaneous acceleration, similar to the instantaneous velocity, is actually the acceleration when we start reducing the time interval to a very small value, or to the limiting case that it goes to zero. When we make sure that the delta t goes to zero in the limit, then this ratio delta v over delta t becomes the instantaneous acceleration. This above equation really is again a definition of the derivative. It is the first derivative with respect to time for velocity. So we can say that the instantaneous acceleration, in physics we Whenever we write acceleration, we mean to say it is instantaneous acceleration. So acceleration at any instant is basically the first derivative of velocity. We know, we have already covered that the velocity is the first derivative of the displacement vector r. Then we can say that acceleration is also the second derivative of the displacement. Acceleration is the rate of change of velocity, and in component forms, this has three possible components for the three-dimensional space. Ax, which is dvx over dt, the acceleration along x-axis. Acceleration along y-axis is dvy divided by dt as a acceleration along the y direction, and a z component is dvz divided by dt. The dimension of acceleration is the length divided by the time square. Standard international units are meters per second square, and one-dimensional case, if we study, then it can be positive or a negative, and we must use some direction indication in which we will label the positive direction and the negative direction. Since acceleration is dependent on velocity vector, even if the magnitude of the velocity is not changing, only the direction is changing, still we have the acceleration. So we are going to discuss such accelerations in detail in coming lectures, but we must remember that it is the vector. Velocity is a vector quantity. Therefore, change in this vector is going to dictate the acceleration. And if the magnitude is not changing, but the direction is changing, then still we have the change, and therefore the acceleration. Let us do one example to figure out the values using the uh, particle which is moving in xy plane. So it's much easier to study at this stage the two-dimensional case, and we can extend our study to three or many dimensions. As this question says, suppose a particle is moving in xy plane so that its x and y coordinates are changing with time, and the behavior of the change is like this, that x as a function of time is equal to a times t to the power 3 plus b times t, and y as a function of time is given as c multiplied by t to the power 2 plus d. Here I think this must be superscript, so that it is t cube and it is t square. Once we are using this function, then we tell that a is given by 1.0 meters per second cube, and b is equal to minus 32 meters per second, c is equal to 5.0 meters per second square, and d is 12 meters per second. Question is to find the position, the velocity, and the acceleration at time t is equal to 3 seconds. So for solution, the first we write the position vector for any time in three dimensions, and it is r vector equal to x times I unit vector plus y times j unit vector plus z times k unit vector. The position vector at any time in two dimensions is given by this, because for two dimensions z component will be 0, therefore it will be x I unit vector plus y times j unit vector. So I now put the values of the function. X is given by a multiplied by t cube plus b times t, and similarly y as a function of time is given as c times t square plus d, and therefore this vector is now written in this form, where the time is variable and x is expressed as in terms of time, and y is also expressed in terms of time, and therefore we can find out the position for the time t is equal to 3 seconds. We substitute the value of t equal to 3. So here I write 3 to the power 3, and here I write t on as a 3, and here t square is 3 square, and so on. Then I simplify this and I reach at this result that it is minus 69 meters along the x-axis and 57 meters along the y direction. So if I have to draw this, I can show that it will be the negative axis, x-axis, and it will have a value of 69 units on the graph paper from 0 in the negative y direction. But it will have a positive vector value along the y-axis, and it will show as a 57 meters or 57 units on the y-axis. We move further. For the velocity component, if we want to find out the velocity, we are given with this r, which is xi unit vector plus y times j unit vector, and I substitute the function a t cube plus b into t times I c t square plus d times j. Then substituting the 3, we have reached at the value of this vector. Now we take the derivative. Taking the derivative means that we will take the derivative of x with respect to time and derivative of y with respect to time. I unit vector is a constant thing and j unit vector is also constant, so they will not have any derivatives. Therefore, they are taken out of this. Once we write it in further form, then this that time derivative will be on a t cube plus b into t, and the time derivative will be on c t square plus d. So if we are going to write the values, I take the derivative. For this derivative, it is 3 times a multiplied by t square. The derivative of t cube is 3 times t square. Similarly, the derivative of t is 1. Similarly, derivative of t square is 2 times t, and the derivative of constant is 0. And therefore, simplifying this and substituting the value of t equal to 3 seconds, I start substitution and reduction, and I reach at the velocity, two components of the velocity, vx I unit vector plus vy j unit vector, as minus 5 meters per second and 30 meters per second. This is along x-axis and this is along y-axis. So the complete vector is now known. Always keep in view that we will substitute the value of t at the end. In the beginning, we will not substitute. We will first take the derivative and solve and simplify and then substitute the value of t. Now we come for the part which is accelerations part. dr over dt gives us the velocity, but dv over dt gives us the acceleration. So dvx over dt, dvy over dt are the acceleration components along x-axis and acceleration along y-axis. Now I substitute I have this velocity vector which is 3 times t square multiplied by a and 1 multiplied by b, and here in y direction we have 2 times c into t plus 0 times d, and then I take the derivative again, then t square derivative is 2 times t and the constant derivative is 0. T's derivative is 1 and therefore it is equal to 2 into c into 1. So I simplify this first and then substitute the value of t as 3 seconds now after taking the derivative. Once I substitute, I reduce the whole thing. It is 18 meters per second square along x-axis and it is 10 meters per second square along y-axis. The complete vector is written as this, with the I unit vector multiplied with the x component and j unit vector multiplied by the y component, and the total vector a vector is shown here. You can see that both a and the ax and ay both are positive. So it is really positive acceleration along x-axis and positive acceleration along y-axis. Remember that the particle which is moving with the constant velocity, it indicates that the instantaneous velocity at any time or any time interval remains the same as that of the average velocity. Mathematically, we can write that the Vx, which is the slope of this, because it is a constant velocity. So on a graph paper, which is the position versus the time graph paper, in which the position is changing with the time and it is going up, the x value is increasing in positive manner, then the slope is given by delta x over delta t, and you know that the straight line has the slope like this. And once delta x over delta t is the slope, which is equal to the velocity along the x-axis, it is basically the x final minus x initial divided by delta t. So I can rearrange the whole thing in the form of the final position equal to the initial position plus velocity multiplied by delta t. So what we want to emphasize here is that the particle which is moving with the constant velocity, it is the motion of the particle uh, shown as a red marked line. Then the slope of this graph is the value of the constant velocity, and y-intercept, which is here as xi. Y-intercept is xi, which is the initial value of the position at time t is equal to 0. Okay, for a constant velocity, the particle has a constant speed. Particle can move with the constant speed along curved path also. So we must remember that the model is the particle under a constant speed. The main equation is that of the average equation, and we can also write the average speed in the manner d divided by delta t. D is the distance traveled during the time interval delta t. For solving the problems related to the motion of particle, kinematic equations are used. Whenever there is a uniform acceleration, we can employ the kinematic equations, and the kinematic equations are generally used to solve one-dimensional problem, two-dimensional problem, and three-dimensional problem. We can use any of the equations or any two of the equations to solve one problem, so that you can have different routes to reach at the result, but the result will be same. Many times there will be more than one way to solve a problem. Let me, without going into the derivations of the details, show you the kinematic equations. The nomenclature is generally this, that the final will be indicated by F and the initial will be indicated by a subscript I. This first equation shows us that the final velocity is equal to the initial velocity plus acceleration times t. And this kind of equation is showing us basically a definition of acceleration. You can determine the object's velocity at any time, the final velocity, using the initial velocity and acceleration and time. For second equation, the average velocity is given by the final velocity plus the initial velocity divided by 2. For constant acceleration, this is just the arithmetic mean of the initial and the final velocity. Third equation is about the final position minus the initial position equal to the average, the definition of the average. We have already defined the average velocity as the difference of the final position minus an initial position, or in a vector form, the displacement vector at final position and the displacement vector at initial position. and the difference gives us the displacement divided by delta t gives us the average velocity. So this is the average velocity's definition in third equation. Fourth equation is an equation which gives us the final position in terms of the initial position xi plus velocity along x-axis multiplied by t plus acceleration in the x direction multiplied by t square by 2. So this can give us the final position using velocity and acceleration. The fifth equation is in which the final position in terms of the acceleration and the displacement. Here no time is involved. We can see there is no time which is coming out of this equation. So we can, if we don't know the time during which this occurred, we can use this to find out the final velocity in terms of initial velocity and acceleration and the positions. Let me briefly talk about the different types of graphs that are occurring. First graph is the graph for the displacement versus the time. This curve, the red colored curve, is showing the displacement as a function of time. And this slope, you can see the slope is the velocity. The green colored line is the velocity. So the curved line indicates that the velocity is changing. Here we have this velocity, another position has another velocity. Therefore, change in velocity is also occurring because green line is changing. Therefore, we can safely say that there is acceleration because change in velocity for delta t time is going to result in acceleration. The graph for this velocity versus time is again shown in the second part, and the slope is giving us the acceleration because this is velocity graph as a function of time. And here straight line is indicating that we have a constant acceleration, although there is an increase in velocity, but the acceleration is constant because slope is 1. It is not changing. The graph for the acceleration versus time, this is the third graph. We see a constant line which is parallel to x-axis. X-axis is t. So for any t, this value is constant. Another t value is still this acceleration is constant. So this straight line is indicating a constant acceleration, and its slope is 0. Now let us do one example on free falling bodies. Free falling bodies are really showing, we have seen many times whenever a object is allowed to be dropped, it moves towards the earth. So free fall is where the acceleration towards earth happens and the body is generally dropped from rest. Then its initial position and its velocity you can start and take as a 0. A free fall also means that there is no drift and there is no friction and there is no air resistance. So question is to find out the position and velocity of the body after 1 second, 2 second, 3 second, 4 second. So from this question, the statement of the question, we first write down and make up our mind to express that the vertical drop is taking place, therefore y coordinate will be employed. And y0 is equal to 0 will be our initial starting point. v0, the initial velocity is 0 because it is starting from rest. Then we are going to use this distance equation. We showed you in previous slide the x equal to x naught plus v naught into t plus half a into t square. But here I have written with the new name y. Y is equal to y naught plus v naught into t minus g t square divided by t. Remember, this minus g is actually the acceleration I have replaced acceleration with the minus g, and minus means that from the zero position it is coming down in the decreasing values of y. And if it was increasing values of y, then g could have been positive or acceleration could have been positive. Here the case is where minus g is the downward motion acceleration. Now we substitute, put value of t is equal to 1 in this and the v0 equal to 0, y0 equal to 0. I get the value of y after 1 second minus 4.9 meters. Then I go further and try to find out the velocity of the falling body at time t. After zero time, of, uh, the particle is moving down and 1 second passes, then I may calculate the final velocity equal to the initial velocity minus g into t. Here again acceleration is written as minus g and multiplied by t. So 0 minus g value, which is 9.8 meters per second square, acceleration is in meters per second square, and it is multiplied with the time value equal to 1. So the answer is minus 9.8 meters per second. In similar way, we can find the values of y and v for the other time 2 and 3 and 4. So I have this table in which the time on this column is 0, 1, 2, 3, and 4. And the position calculated initially 0, minus 4.9, minus 19.6, and so on. And we see that the position is with the negative sign, it is going to increase from 4.9, 19.6, 44 point, but in the negative direction. Similarly, the velocity is calculated, the final velocity at time t is equal to 1, 2, 3, and 4, and it is 9.8, 19.6, 29.4, 39.2, all with the minus signs, which is showing that it is the vertical downward velocity, and the difference between the two velocity is a 1 second, and after the 1 second's interval it is with the increase, or the difference is 9.8 meters per second. The acceleration is what the next will be, and it is 9.8, 9.8, 9.8. This is a constant acceleration. So I can safely say that the average velocity during each 1 second interval is basically the displacement of divided by the time interval, and it is really behaving like expected. Remember that in kinematic equations, or the use of the kinematic equations, we are not really bothered about the force or the external forces or the types of the forces involved. We are only considering the motion, the position change, the velocity change, or any change in acceleration. So that's the kinematics. As soon as we move from kinematics to dynamics, then dynamics of the bodies will be studied under the external and internal forces. And we will start balancing the forces. We will start understanding how many forces are applied, what direction they are taking, and what is the net effect. That is going to be in the coming lectures. So here we are not really considering the force because we are only studying the kinematics. I will stop here, and these slides are ended, and I will continue my discussion on the applied physics, on the nature of the forces and the Newton's law and the kinematics and the application of kinematics in coming lectures. Thank you so much.